Welcome to the 11th IEEE Innovation Smart Grid Technologies Asia Conference. Have you ever thought how to overcome various power losses or surges in the system due to high demand? And what are the resources utilized in the system to overcome these problems? I am Misha and I am going to do a video presentation on the title Power Loss Reduction in Distribution Systems in the Presence of DGs and EVs on behalf of me and my teammates. Our main inspiration is the rapid increase in the demand for electrical power in the country. Along with that, high power losses, low voltage stability index, and high voltage drop. This provides a motivation to integrate DGs into the radial distribution network, which are majorly renewable energy resources. Our objectives are as follows. First, implementing GA in standard IEEE distribution network to minimize network power losses and simultaneous improvement of voltage profile upgradation. Second, investigating the presence of EVs along with the DGs in the distribution system. The following slide shows the mathematical model we chose to find the optimum sizes of DGs, which are determined based on the penetration level of the DG into the network. Further, the penetration level is defined as power generated by DG divided by power generated by DG along with the real power generated by the grid to the load. We have used 5-step genetic algorithm. The steps are being defined further, the two of which are discussed in this particular slide. First being the initial population. In this, an individual solution is defined as a matrix of x1, x2 and x3, where x1 is penetration level, x2 is the location index, and x3 determines type of DG. The second step is selection. So here xi and xj are two selected individuals from parent x, and ci and cj are the values returned by the objective function. So if P is the set of all parents that have the chance to reproduce, so Xi belongs to P only if Ci is less than or equal to Cj. Here penetration level is considered as lesser than 50%, and location index is like we have used 33 bus system or 69 bus system. So X will be less than 33 or 69. The type of DG is synchronous generator, that is X3 will be constant and will be 2. In this particular slide, the other 3 steps are being discussed. The third one is reproduction. So here from all the possible parents P, Pi and Pj are selected and the matrix is formed. The fourth step would be crossover. Here K be the selected crossover point and K will be greater than 1 or equal to 1 and would be less than or equal to 3, and O1 and O2 will be the two crossover children from parents Pi and Pj. The fifth step would be mutation. So after a given population X, a mutant child M is obtained by selecting a random individual Xi from parent X, and one of the genes of Xi is randomly selected and changed. The particular slide shows the flow chart of our mathematical model. So first would be creating the initial population, and next would be the evaluation of objective function. So if objective function reaches the convergence, the locations which would be obtained as an output would be the optimal location, and the flow would end here. If at all there is no convergence, then there would be a series of process followed, which will be selection, reproduction followed by mutation. So the next generation would be produced, and again this objective function evaluation will take place. This will take place until the convergence is reached. Once it is reached, again that output would be our optimal location. This particular slide shows the data which we have used during our entire process. We have used standard IEEE 33 bus system and also standard IEEE 69 bus system. The following slide shows the line data along with the bus data for 33 bus system which we have used in our process while we were doing trials. So we have considered these information and we went through the trials. The following slide shows the line data for 69 bus system. This particular slide shows the bus data for 69 bus system. This slide shows the graph of load versus time. So basically it's a loading condition. So we have used two scenarios with varying loading conditions, and we are going to test upon these two scenarios separately for both 33 bus system and 69 bus system. The slide talks about the result. So first we are going to look upon the IEEE 33 bus system scenario 1. So this tabulation is formed from taking the results from the model which we have used, that is GA model. Here we have 5 columns. The first column is for time, which denotes the hour, like first hour, second hour, to up to 24 hours. We have also considered 4 cases. That is losses without DG is the first one, that is base loss. The second case is losses with DG. The third case is losses with EV and without DG. The fourth case is losses with both EV and DG. We have recorded the values and formed the table. The slide shows the tabulation for IEEE 33 bus system scenario 2. In order to get some conclusion, we have compared both the tables, and we have got to know a very interesting thing. That is, for 19th hour of the day, the variations are similar in both the scenarios. So we are going to compare. So let's talk about 19th hour. First, we'll talk about case 1 versus case 2, that is losses without DG versus losses with DG. So the loss has decreased because here DG is going to supply the desired load, so the loss has reduced. Next, comparing case 1 with case 3, when we are incorporating EV alone in the system, there is an increase in the loss. When we are comparing case 1 versus case 4, that is EV and DG both are present in case 4. So when we check there, again the loss has increased, because at this point the EV is drawing power. So when EV is incorporated with the renewables, then loss is reducing compared to the base loss, because DG can charge the EV and supply enough power to reduce the losses. So after IEEE 33 bus system, we move to IEEE 69 bus system. This particular slide shows for scenario 1. So the table here is for scenario 1. So when we consider 9th, 11th, 20th and 21st hours of the day, there is a reduction in loss for case 2, because there is a placement of optimal sized DGs in optimal location. In case 4, the losses are varied even having the same base loss, that is of case 1. It is due to the variation in the power of EV. The following slide shows the tabulation for IEEE 69 bus system scenario 2. Also, we have noted down some of the observations. So here we have considered 19th hour of the day, and we saw that the variations are similar in scenario 1 as well. Like they both show the same variation pattern. In the 19th hour, when we compare case 1 and case 2, the loss have reduced in case 2 since DG supplies the desired load. When we compare case 1 and case 3, the losses have increased because EV is charging. So EV acts as a load, therefore the loss has increased. Whereas when we compare case 1 and case 4, the losses have reduced because here EV is supplying power along with the DG for 19th hour, which also happened, like the similar pattern was seen in scenario 1 as well. After looking on every tabulations and graphs, we have got to conclude few things. The losses in case 2 is lesser than in case 1, majorly because DG is supplying the desired load. After incorporating the EVCS in the system, the variation is seen in the system due to variation in the load value, and furthermore, EVCS is incorporated with the DGs, which eventually reduces the losses because EVCS is discharging here. The next 2 slides shows the references which we have used while we were doing the trials and when we had to refer to something, may it be mathematical model or the approach to write down the code and all those stuff. Thank you so much for giving us the opportunity to showcase our paper and do a video presentation in the conference. Along with that, I would also like to thank all the listeners for listening to me patiently throughout the video. Thank you so much and have a good day.